Hello everyone, welcome to GMAT Point. I'm Prakhar Jain and today we'll be learning about the absolute value function. So let's get started. The absolute value function is a fairly simple concept, but it's also one where students can make a lot of silly mistakes because there are a lot of minute details in it. For example, if I'm an examiner and I'm making, let's say, an algebra question and I wanted to add an extra layer of difficulty or an extra trap for the student, the absolute value function is definitely one of the tools I would go to. It's a very prominent topic in quants. Obviously, it's a mathematical concept, so it appears a lot in quants. But also, it's a very prominent topic in data sufficiency questions in the DI section. We'll see further in the video how the questions are framed in data sufficiency. Now, what is the absolute value function? At its core, the absolute value function tells you about distance. So, for example, if I was to write mod of 3, this gives me the distance of the number 3 on the number line from the number 0. And this distance would be 3. If I was to write mod of minus 3, this would tell me the distance on the number line from the point 0 to the point minus 3. And because distances can only be positive, right? So you can't have minus 2 kilometers. This will be also 3. So mod of minus 3 is also 3. So if you think about it, what I'm doing here with the absolute value function is I'm taking a crucial piece of information away from you. Say for example, you wanted to go from point A to point B, not on the number line, just in general you wanted to go from point A to point B, and you asked me what the route was and I just said, okay, point B is 10 kilometers away, but I didn't tell you what direction those 10 kilometers had to be traveled in. So I've taken a crucial piece of information away from you. And this is usually around this is the concept around which the data sufficiency questions are framed, because they are about information. Taking away a piece of information makes it a prominent topic in data sufficiency. Now this is the notation for mod. Mod, by the way, is short for modulus, which is another term we use for the absolute value function. So if you think about it, if x is greater than or equal to 0, right? If x is greater than or equal to 0, then the distance is already positive, right? From 0 to 3, if I'm finding mod 3, then it is just the number inside the mod. So if x is greater than or equal to 0, this becomes x itself, right? There's nothing that needs to be changed. But in the case that I had 0 to minus 3, this distance was 3. So if the number inside the mod is less than 0, then this has to be minus x. Because if I want to convert minus 3 to positive 3, then I must multiply this with minus 1 again, right? So if x, the variable inside or the number inside the mod function, is a negative number, the mod function returns you the negative of whatever's inside it. So now let's look at some example questions. The first example is how many integers can satisfy the inequality mod x is less than 3. Now we saw that there are two possibilities whenever you're dealing with the modulus function. In the first possibility, you have x greater than or equal to 0. In the second possibility, you have x less than 0. So if x is greater than or equal to 0, we have mod x equal to x, which means the inequality now becomes x greater than or equal to 3. But at the same time, x less than 3. At the same time, x must also be greater than or equal to 0. So the overall inequality becomes x is less than 3 but greater than or equal to 0, and x must be an integer as well. So the possible values I have are 0, 1 and 2. Right? Now let's look at the second case. If x is less than 0, then I have mod x is minus x. So my inequality becomes minus x is less than 3, which gives me x is greater than minus 3. But at the same time, x must also be less than 0 because that was my assumption for this case. So I now have x greater than minus 3 but less than 0. And because x must be an integer, the overall solutions I get are minus 2, minus 1, and that's it, because I can't be equal to 0 over here. The number of possible integers I have is 3 integers from here and 2 integers from here. So the answer is 5. Now let's move on to the next example. Example 2. What range of values satisfy the inequality mod x plus 2 is less than 5? Again, two possible cases. The stuff inside the mod being greater than or equal to 0, which means x must be greater than or equal to minus 2. This is the assumption. In the second case, we will have stuff inside the mod less than 0. So x less than minus 2. In this case, we will get x plus 2 less than 5. So x is less than 3. Again, combining the two, the assumption and the conclusion, we get x less than 3 greater than equal to minus 2. This is the first range. In the second range, we get x is less than minus 2 and the stuff inside the mod is negative. So we have minus x minus 2 less than 5. So we have minus x less than 7 or x greater than minus 7. Again, combining the two, we have x greater than minus 7 and less than minus 2. So this is the second range. But if you think about it, the range I have got from this one, for example, if I was to draw the number line, the first case lets me go from minus 2 to 3. So it lets me go from minus 2 to 3. This is from the first case. The second case lets me go from minus 7 to minus 2. So I have minus 7 over here and I have this distance. And equal to minus 2 is allowed as well. So effectively, if you think about it, my entire range is just minus 7 to 3. So my answer is x belongs from minus 7 to 3 and it cannot be equal to 3 or minus 7. Now let's look at the number line way of solving this example. So let's say I had x plus 2 is less than, mod of x plus 2 is less than 5. In this case, the the stuff inside the mod was splitting around the value x equal to minus 2, right? If I had x equal to minus 2, if x was bigger than this, I had the stuff inside to be positive. If it was less than this, I had stuff inside to be negative. So in this question, what I'm effectively asking is that for what range of values of x is the distance of it from minus 2 less than 5? Let's try and draw the number line and try to understand this. So I have x equal to minus 2 over here. What this question asks you is what are the range of values of x for which the distance from minus 2 is less than 5 units. Again, because distance doesn't care about direction, we can go 5 units in this direction and 5 units in this direction. Minus 2 and then minus 5, because this is leftwards, would be minus 7, and minus 2 plus 5 rightwards, this will be 3. So as you can see, we get the same range. X belongs from minus 7 to 3. Because this was a simple enough question, the number line method is a little bit more effective. But in difficult questions, the number line becomes a bit too complex. In the first example, again, if we were to look at the number line, the distance in this case would be 0 because x greater than 0 changes the sign and x less than 0 changes the sign. So the point around which the signs change is x equal to 0 in this case. So what the question is asking you is for what range of values of x is the distance less than 3 from minus 3 to 3, right? Any point, for example, this point will have a distance less than 3. This point will also have a distance less than 3. So the range for x in the first case was x goes from minus 3 to 3. Right? Now let's look at why the points around which the sign changes matter. So these are called critical points. Critical points are the points around which a function changes its sign. Now in the examples we've looked so far, there was only one critical point, right? In mod x plus 2 less than 5 example, there was only one critical point at x equal to minus 2. But there can be questions where there are multiple critical points. That's when the number line method becomes a little too complicated. So the method for easy questions is the number line, as you saw in the previous slides. It was much easier and much faster to use the number line method than to use the critical point method. But in the case that you have multiple functions and multiple critical points, it becomes much more easier to just use that method. It's more of a one size fits all method, right? Every question you can solve to critical points. Now let's look at this example. We have mod of x minus 1 greater than mod of x minus 2. So, okay, we'll have in this case two critical points. At x equal to 1, this will change its value. So for example, x minus 1 greater than equal to 0 gives me one case here, and x minus 1 less than 0 gives me another case. So x greater than equal to 1 is what this simplifies to, and this simplifies to x less than 1. So as you can see, around the point 1, this function is changing its sign. If it was this case, it would give me x minus 1. Mod x minus 1 would give me simply x minus 1. But in this case, it was changing the sign. So mod x minus 1 would have given me 1 minus x. So you can see it changes the sign. So if for this one, x equal to 1 is a critical point. Similarly, for this one, x equal to 2 is a critical point. So I have two critical points, which are 1 and 2. Now, so we will have effectively, instead of having multiple cases, one for this and two cases for this and two cases for this, I can now simply have three cases. So the cases can be simplified to x greater than equal to 2, which is this region over here, x less than 2 and greater than equal to 1, and the third case, which is this region over here, and the third case will be x less than 1, which will be this region over here. So now let's try to solve this question. If we have x greater than equal to 2, I know x minus 2 will be positive, right? Because the critical point was 2. Right of that, we have this as positive, and this had the critical point 1. So right of 1 is also positive, which means both of them will be positive in this case. We will have x minus 1 greater, the inequality will have as x minus 1 greater than x minus 2, which gives me minus 1 is greater than minus 2. Because this is a true statement, this is completely true, right? This is always true. This means this is a valid range. So x greater than equal to 2 is one range of values that we have. In the second example, we have x greater than equal to 1 but less than 2. Since x is greater than equal to 1, this will be positive, but this will be negative because x is less than 2. So we will have x minus 1 greater than 2 minus x, which gives me x greater than 3 by 2, which is just 1.5. So in this case, again combining the two, we have that x must be greater than equal to 1, but also x must be greater than 1.5. So I have x must be greater than 1.5. So I have x greater than 1.5, but the upper limit is from 2 over here. So less than equal to 2. So that is my second range. In the third range, I have x less than 1. So both of these will be negative now, which gives me 1 minus x greater than 2 minus x, which gives me 1 greater than 2, which is a false statement. So for no values of x less than 1, is this going to be a valid region? Again, if I was to combine these two, this one says that 1.5 to 2 is fine, and this says anywhere above 2 is fine. So if I combine the two, I basically get x greater than 1.5 as my solution. Again, if I was to use the number line in this case, I would have had 1 and 2 as my critical points. And what the question is asking you is that for what range of values of x is the distance from 1 greater than the distance from 2? Let me just draw this slightly higher up. So the question asks you, what range of values of x do you have such that the distance from x equal to 1 is greater than the distance from x equal to 2? Now, first let's look at the midpoint. The midpoint will be at 1.5. We know for a fact that if I was to move anywhere to the right of this, like at this point, the distance from the two sides is equal. If I was to move any more right, that would increase the distance from 1 but decrease the distance from 2. So anywhere right of 1.5 to 2, which is basically just saying x greater than 1.5 and less than equal to 2 is fine. If I was to move rightwards of 2, the distance from 1 will become, for example, this distance, and distance from 2 will be this distance. So x distance from 1 is again greater than that. So my other solution will be x greater than or equal to 2. And if I was to now move leftwards of this, then the distance from 1 at this point will be like so, but distance from 2 will be like so. The distance from 2 is larger, so this is not a valid range. And leftwards of 1, let's say I had this point, distance from 1 is this, distance from 2 is this. So again, not true. So the only two solutions I have are these. Combining these, I get x greater than 1.5. So if you think about it, anywhere right to the middle point of 1 and 2, the distance from 1 is higher than the distance from 2, and so that is a valid range. Now, again, you can solve this question using the number line or critical points. In this case, you had two critical points. So the number line one again was fairly straightforward, but it took a lot more effort. Again, you can probably see that there are a lot of points where you could have made a mistake. Maybe you would have like this requires a lot of imagination or a lot of drawing, and you have a basically your chances of making a mistake with this method are a lot more than your chances of making a mistake with this one. Can you use either method? Yes, 100%. But is there a particular method I would suggest you should use? Yes. If you have more than one critical point, stick to critical point method. Now let's move on. Now let's look at the graph of the absolute function. What is the graph of the absolute function? So we have an image over here, but we'll try and derive it ourselves. So first of all, again, we have two cases because absolute value function always comes with two cases. So if I have, let's say, y equal to x, right? So, okay, before that, we have mod x, right? Mod x is x if x is greater than equal to 0 and minus x if x is less than 0, right? Now, let's say we had y equal to mod x, right? This is the graph we are trying to make. So, if x is greater than or equal to 0, we get y equal to x. So, we'll draw the graph for that, but only for x greater than 0, greater than or equal to 0. This is our origin here, x-axis and y-axis, right? For x greater than 0, which means right of the y-axis, we have y equal to x, right? That gives me the graph for y equal to x. But if x is less than 0, which means left of the y-axis, we have y equal to minus x. What is the graph for y equal to minus x? It looks like so. So just for this region, I would get this. We can see, so this was minus y equals minus x, which is the same as this graph over here. So the graph for the absolute value function looks like so. If it's to the right of the origin, it's y equal to x line. If it's to the left of the origin, it's y equal to minus x line. We'll just note that down over here as well. Y equal to x and y equal to minus x. Now, let's look at an example question. We have mod x less than 2, right? Now, earlier we would have done this using the number line, but we can also do this using the graph. So, we have mod x graph over here, absolute value function graph over here. And if I was to now draw the y equal to 2 line, it would be like so. So this is my y equal to 2 line, right? The question is mod x less than 2. So where is the graph of absolute value function lower than the graph of y equal to 2? It is this region over here. Now, if you think about it, y equal to x and y equal to 2 would intersect at the point x equal to 2, and similarly, these would intersect at the point minus 2. So, the answer would be x will be from minus 2 to 2. Oh, and the values 2 themselves would not be included because it is less than. If this was less than or equal to, then yes, it would have included the extreme values as well. Now, we'll look at some questions. So, for the first question, we have if mod of x is equal to mod of y, which of the following is true? First of all, we'll start making cases. If we have, again, we have two absolute value functions. So we'll have x greater than equal to 0 case. Actually, we'll have four combinations. So we'll have x greater than equal to 0 and y greater than equal to 0. Second case will be x stays greater than equal to 0, but y becomes less than 0. Third case will be x is less than 0, but y is greater than equal to 0. And the fourth case will be x less than 0 and also y is less than 0, right? So in the first case, we have x greater than equal to 0 and y greater than equal to 0. So we have x equal to y. That's fairly straightforward. In this case, we'll have x positive and y negative. So we have x equal to minus y. In this case, we'll have minus x equal to y, which is just x equal to minus y again. And in this case, we'll have minus x equal to minus y. So x equals y. So all in all, these two cases are the same and these two cases are also the same. So the two cases are x equal to y and x equal to minus y. Right, now let's look at the options. Is x over y always going to be 1? No. It is going to be true for this case because we'll get x upon y equal to 1. But in this case, we'll have x upon y equal to minus 1. So this is not our answer. Similarly, option B is also not our answer because it's not necessarily true. Is x square be going to is x square going to be equal to y square? In the first case, x equal to y will have x squared equal y squared. So that is true. In the second case as well, when we square both sides, the negative goes away and we'll have x square equal to y squared as well. So this is always going to be true. Let's look at the remaining two options as well. X cube equal to y cube. We have x equal to y, which would give me x cube equal to y cube. So it works for the first case. But in the second case, when I am to cube a negative number, it would give me x cube equal to minus y cube. So this need not be true. In the fifth case, we have x to the half is equal to y to the half. Now, most of you might already know, but for those who don't, raising a number or a variable to the half power is just the same as square rooting it. So we have root x equal to root y. Now, in the first case, this would be fine, right? Because I have x equal to y and they're both either greater than equal to 0 or both less than 0. Because I can now have a negative number on either side. For this case, I could have both negative, or for either of these cases, I could have one of them as negative. This means that for 3 of the 4 cases over here, or basically any case that gives me this, and one case which gives me this, uh, in this case over here, for these 3 cases, the square root is not even defined. So let alone talking about whether or not they are equal. So this option is simply invalid. It's not even just a wrong option. It's invalid in a lot of our cases. Let's move on to the next question. Find the range of values of x for which mod of x minus 1 greater than mod of x minus 5 holds. Since this has two critical points, we'll do the number line method and we'll also do the critical point method. So first, let's look at the critical point method. What are what are the critical points going to be? We have x minus 1 greater than equal to 0, which means x greater than equal to 1, or we have x minus 1 less than 0, so x less than 1. So one of the critical points will be 1. Similarly, over here, the critical point will be 5. You can do this calculation for yourself. It's the same as this over here. Now we get three regions. We have x greater than equal to 5. Then we have between these two. So we have x greater than equal to 1 and less than 5. And in the third case, we will have x less than 1. Right. So in the first case, we have x greater than equal to 5. Both of these will be positive. So I have x minus 1 greater than x minus 5, which gives me minus 1 is greater than minus 5. This is a true statement, always true. So this works. So x greater than equal to 5 is one of the ranges I will get. In the second case, I have x minus 1, mod of x minus 1 will be positive, but this would be negative. So I have x minus 1 greater than 5 minus x. So solving this, I'll get x greater than 3. So combining the two, the lower limit on x is 3, higher limit is 5. So I have x greater than 3 and x less than 5. This is going to be my second range. In the third case, I have x less than 1. So both of them are going to be negative this time. Since both of them are negative, I have 1 minus x greater than 5 minus x, which gives me 1 greater than 5. This is a false statement. So this region, there are no valid solutions. If I combine the two, so this one tells me that anywhere between 3 to 5 is fine. And this tells me that going rightwards of 5 is also fine. Combining the two regions, I get x greater than 3 as my answer. So our answer will be option C over here. Now let's look at the number line method. Now, basically, the question asks, for what values of x is the distance from 1 going to be larger than the distance from 5? As we saw in the previous example, anywhere right of the middle point is fine, right? Because anywhere right of the middle point less than 5, let's say this point, the distance from 1 is like so, and the distance from 5 is like so, so this works. So anywhere between 3 to 5 is fine. So my region comes out to be x greater than 3 less than equal to 5. And for the second example, if I am going anywhere right of 5, let's say this point over here, distance from 5 is that, and distance from 1 is that, which is clearly much larger than the distance from 5. So the second case gives me x greater than 5, which gives me, combining these two, I get x greater than 3. And anywhere left of 1 or anywhere even left of 3, if I am anywhere left of 3, let's say this point, this is the distance from 1, but this is the distance from 5. So anywhere left of 3 won't work. So x greater than 1 less than 3 is not a valid region. And for the fourth region, which is going to be left of 1, I have, let's say this point, distance from 1 is that, and distance from 5 is that. So again, the value will not hold. So x less than 1 is also not a valid region. So we can see our answer using the number line method is the same. X is greater than 3 and less than equal to 5. Let's look at the next example. The next question we have is the data sufficiency one. So again, this is going to be a prime example of how data sufficiency questions are framed around the absolute value function. First, we are given that mod of y is equal to x plus 1, and the question is x equal to 0? The first statement says that y is greater than or equal to 0. Okay, let's test this one out. We have mod y equal to x plus 1. Since y is greater than equal to 0, this simplifies to y is equal to x plus 1. And the question is asking me about the value of x. So I will simplify this, or I will rearrange it to get to x on one side. X will be y minus 1. Now I know that y is greater than or equal to 0, which means the minimum value of y is x, of y is 0, which means the minimum value of x must be minus 1. This gives me anywhere right of minus 1 as a valid region for x. Now this can have multiple values. 0 is only one of them. So I cannot answer the question, is x equal to 0 definitively with statement 1. So statement 1 alone being sufficient is not going to be true. And also each statement alone is sufficient is also not going to be true, because I know at least one of them is insufficient. Right? Now let's look at statement 2. Statement 2 is that x is a non-negative integer. This on its own doesn't tell me anything. X being a non-negative integer could give me 0, 1, 2, 3, any value. 0 is also a part of them, so x may or may not be equal to 0. So this tells me that this is meant to be statement 2 alone, and this is meant to be statement 1 alone. So statement 2 alone is sufficient, but statement 1 is also not true, because statement 2 alone is not sufficient. Now let's look at the combination of the two. From the first statement, my possible answers were x greater than equal to minus 1. But I did not even know that x was an integer or not. In the second case, in the second statement, my possible solutions were anywhere right of 0. So I had, and also that x must be a non-negative integer. What are the non-negative integers that statement 1 allows? Statement 1 allows, it does not allow minus 1 because that's a negative integer. A non-negative integer it allows will be 0, but so will be 1, so will be 2, so will be 3, and so on. Again, combining the two, it's not enough information. X may or may not be equal to 0. So our answer is E. Both statements together are not sufficient. Let's look at question 4. How many integral solutions does this one have? Now, in this problem, before we get started, I want you to notice a couple things. First of all, there are 3 critical points. With 2 critical points, the number line method was complicated enough. With 3 critical points, it's going to be harder still, right? And also, up until now, we have seen x minus 3 or x minus 2 or x minus 1 or x minus 5. In this case, we have 3 minus x. This is where the number line method becomes even more complex. What starts happening is that the values where you are positive and values where you are negative swap sides. So positive becomes to the left and negative comes to the right. So it makes things a lot more complicated. So for this question, we'll stick with the critical point method. So let's look at the critical points. Our critical points from here will be 1, 2, and 3. So we have 1, 2, and 3. The first region is x greater than 3, greater than or equal to 3. Second region is between 2 and 3. So x greater than equal to 2, less than 3. Third region will be between 1 and 2. x greater than equal to 1 less than 2, and fourth region will be left of 1, so will be x less than 1. Right, so if x is greater than equal to 3, this is positive, so I have x minus 1. This is going to be negative in this case, because if I have x to the right of 3, for example, if I have x equal to 4, 3 minus 4 is going to be negative, right? Because this is flipped, so we'll have x minus 1 minus from here, and then the negative of this, so minus x minus 3 is equal to x minus 2, which is going to be positive in this case, x minus 2. Simplifying this, I get, these cancel out, I get x, x is equal to 4. So we get that as a possible solution. We can try and put this in the equation to check our answer. 4 minus 1 is 3. 3 minus 4, and then the mod of that is going to be 1. 3 minus, and 4 minus 2 is going to be 2, mod of which is 2. So 3 minus 1 is 2. That's true. So x equal to 4 is a valid solution. Let's look at the next region. Now, in this region, I am going to have x minus 1 positive, x minus 2 positive as well, because we are to the right of 2. But also this one now, again, left of 3 and greater than 2, let's say 2.5. 3 minus 2.5 is plus 0.5, which is positive. So this is now going to be positive as well and going to stay as it is. We'll have x minus 1 minus 3 minus x is equal to x minus 2. This now simplifies to 2x minus 4 is x minus 2, which gives me x is equal to 2. So x equal to 2 is also a valid solution. Again, let's try putting x equal to 2 in the equation. We get 2 minus 1, which is 1, mod of which is 1, minus 3 minus 2, which is 1, mod of that is also 1. 2 minus 2 is 0, and we can see 1 minus 1, 0. So that is a valid solution as well. So we have two values so far. Let's look at the region from 1 to 2. Now, right of 1, so this is going to be positive. Left of 2, so this is going to be negative. And again, between these two, let's say 1.5, 3 minus 1.5 is positive. So this is also going to be positive. So we have x minus 1 minus 3 minus x is equal to 2 minus x. This gives me 2x minus 4 is equal to 2 minus x, which means x is equal to 3. But if you think about it, x is equal to 3 is outside of our assumed region, right? I get a solution which is outside of my assumption. This means this is not going to be a valid solution. Basically, in this case, what we are saying is that for x to be between 1 and 2, x equal to 3 is a valid solution. That statement makes no sense. I get a solution outside of the range I'm considering, so it's an invalid solution. Last range, x is less than 1. So now this time I will have negative, negative and positive. So I'll have 1 minus x minus 3 minus x is equal to 2 minus x. This will give me minus x and plus x cancel out. This gives me x is equal to 4 as well. But again, this is outside of my assumed region. I'm saying x must be less than 1, and the solution I get from that is a number greater than 1. Again, an invalid solution. So the only possible solutions are x equal to 4 and x equal to 2. So the answer to the question, how many integral solutions, is option B. There are two integral solutions. Now let's move on to the last question. If 3x plus y is 1 and mod of y is less than equal to 10, how many ordered pairs x, y exist such that both of these are satisfied if it is known that x and y are integers? So this is a lot of information in the question, so let's break it down. I am given one equation that must always be true, and I am given a certain constraint on y. Right? I have a lot of values of y, but there are a finite number. This means that x must also only have a finite number solutions. And the reason I know this is a finite number is because I am told that they are integers. If they were real numbers, I'd still have an infinite solutions. So the question won't make much sense. So I have a constraint on y, a constraint on x, and a constraint that interlinks the two. So how many ordered pairs are possible? Let's first look at the possible values of y. The possible values of y I have is that we have mod of y less than equal to 10. So distance from 0 on the number line must be less than 10. This means the region I get is from plus 10 to minus 10, or rather minus 10 to plus 10, right? And because equal to is allowed in this inequality, y must be from minus 10 to 10 with both sides included. In case you don't know from before, square brackets means that the extreme values are also included and you can have those solutions, right? So now let's start testing these values in the equation that we have. So the equation I have is that 3x plus y must be equal to 1. For the first value of y, I have y equal to minus 10. So let's test that. We have 3x minus 10 equal to 1, which means x must be 11 by 3. However, I am told that x must be an integer. This means y equal to minus 10 will not offer me an ordered pair that satisfies all of these conditions. So this does not work. In the second value, I have y equal to minus 9. And I'll just to be on the safer side, we'll write this down as well, that these are integer, that y is an integer. Let me write this down in readable handwriting. Integers, right? In the second value, I have y equal to minus 9. So we have 3x minus 9 equal to 1. We have x equal to 10 by 3. Also not an integer, so not a valid solution. In the third value, I have y equal to minus 8. So 3x minus 8 is equal to 1. X will be 9 by 3, which is 3, an integer. So one pair I can get is 3 comma minus 8. That is one of the pairs. Now, once you found the first pair, right, there is obviously, you could test all of the values, right? It's a finite number. It's not impossible to test them all. You have, I think you have 21 values. You have 21 possible values. You can go over it, right? But there's also a smarter method to it. Let's look at that. So from the equation, I have x is equal to 1 minus y upon 3, right? I know for a fact that 1 minus y must be divisible by 3 for x to be an integer, right? And one of the values I have found is that y equal to minus 8 works. I know that y equal to minus 8 works. And I know that minus 9 and minus 10 don't work, and I cannot go any more left after once I've reached minus 10, right? It means I can only go right. Now, because I have to make sure that x is divisible by 3, the values will occur in increments of 3, right? It will follow the table of 3. If I have minus 8 as a solution, the next possible solution will be 3 points after. So the next possible solution will be at y equal to minus 5. And we can test that as well. X is equal to 1 minus minus 5 by 3 will give me 2. But we can also check, for example, if I tested a value in between, if I had y equal to minus 6 as the value I was testing, I'll have 1 minus minus 6 by 3, which will be 7 by 3, which is not an integer. So instead of checking all the values, I can simply make jumps of 3 until I reach x equals 10, or rather y equals 10. So the values I get will be minus 8, minus 5, minus 2, plus 1, plus 4, plus 7, and plus 10, because 10 is included. Now let's count these up. We have 1, 2, 3, 4, 5, 6, and 7. The answer is there are 7 ordered pairs. The way I think about this question, or the way I thought about this question, is that instead of knowing what the ordered pairs are, the question doesn't ask me what those pairs are. I don't need to calculate x for every one of those pairs. All I need to find is how many ordered pairs exist. The constraint on the first constraint was offered by y. The second constraint was offered by x, that it must be divisible by 3. So I introduce the first constraint, find out the set in which my values must lie, and then I introduce the second constraint to start making like a final shortlist of those numbers. So the answer I got with that is 7. That was the approach we used. Introduce one constraint to shorten your uh, in a way you can call it the area for search, like your searching area, right? So you shorten that with the first constraint, and then you use the second constraint to shortlist it further and get your final answer. So that's it for absolute value functions. If you have any doubts, feel free to drop them in the comments below. We have loads of free mock tests, free diagnostic tests, and question bank and practice questions on GMAT Point. If you want access to those free resources, the links will be in the description. There will also be a link in the description for the formula PDF for GMAT Quants. Thank you and have a nice day.